Good morning, everyone. I'm Ronsi, and I'll be presenting on a topic maxima and minima. It's a very interesting application in everyday mathematics, as we'll see. So, what is maxima and minima? As the name suggests, maxima is the highest point of a function. So now, if you get a function, I've given you an example function. And if you graph this function using any online graphing app, or like if you can graph in your graph books, you'll get a graph. So then the point at which the graph has the maximum curve, that means the graph goes at the maximum highest point, that's known as the maxima of that function. So it's the value of the variable which will give the highest value. So there would be some point in that graph which will give the highest value. So that point is known as maxima, and the value it gives is known as the maximum value. The opposite of minima, it's the opposite of maxima, sorry. Minima is the lowest point of function, that is the lowest point it will go, that is concave down. It's in mathematical terms you can say maxima is concave up and minima is concave down. It's not there in CBSE, just extra I said. So is the value of the variable which will give the lowest value. So the point, the coordinates of the graph which will give the lowest value of the function. So the coordinates will be known as minima, and the value is known as minimum function. So after using the methods which I'll tell later, you'll get maxima of this function as -1 and minima as +1. Don't worry, I'll teach you later. So this is an example of the graph. As I was saying, the graph goes up here and the graph goes up here also. But then if you see, it has reached its maximum extent over here. So this is the local maxima. You can call it as maxima, local maxima also. So this coordinates, these are the local maxima. And you can see here, it goes down here and it goes down. This is the minimum extent it can go. Afterwards, the graph just shoots up and it aligns with the y-axis. So this is the function. It's complex, but then So this is the first method of finding out any maxima or minima value of any function. So the first derivative test. It's a method for determining whether a function's critical point. Critical point is basically the value which you'll get after using this method, whether it's local maximum, local minimum, or neither. There are functions which are undefined, which don't give you any maxima or minima. So first step, the function which you get, f of x, you differentiate it, normal differentiation, and then you get f dash x. So and then after that, the function which you get, the f dash x, you equate it to 0. I have examples later, so if it's complicated now, it's fine, you'll understand later. To get the critical point, so once you equate it to 0, the value which you'll get, that value will be known as the critical point of the function. Now choose values LHS and RHS value of critical point. The critical point, the value which you get, you have to choose intervals, the left hand side, the right hand side. So now suppose if I get value as x is equal to 2. So now the LHS value will be 1, 0, -1, -2, and RHS will be +3, +4, like that. So now take any value. Now if I take x is equal to 1, which is left hand side of x is equal to 2, you substitute it in f dash x, the differentiated one, and then you get the value. The same thing you do with the RHS value, and now you observe the values which you get, like how it's behaving. So now if after substituting LHS value, I get value as, just example, I get value as 0, and after substituting RHS value, I get as -1 or -2 something. So as you can see, it's going from positive to negative. 0 is positive and -2 is negative. So it's going from positive to negative. That means the value which you got, the critical point, is a local maxima, and the value is local maximum. The same opposite. Now suppose if you change it, I got LHS value as -1 and RHS value is 0. Now it's going from negative to positive. That means the value is local minimum. So if no sign change occurs, it's neither maximum or nor minimum. So if I get x as 1 and x as 2 for both LHS, RHS, it's like there's no maxima minima for that. Yeah. Now this is the second derivative test, another method which is easier. Like you can calculate maxima minima in like shorter steps compared to first derivative test. So it's very similar to first derivative, but it's faster. So here you find critical points which I've already done in first derivative, equate to 0, differentiate. Now the differentiated one, you differentiated here once, f dash x, you got f dash x. Now you differentiate that f dash x one more time, second derivative, which double differentiation. You differentiate it one more time to get f double dash x. Now the x in f this f double dash x, you replace it with the critical points obtained. You obtain the critical points here and then you replace it in the function and you evaluate it. So now if the value of the function is greater than 0, then the value which you got is local maximum, or the point is local maxima. Or if it's less than 0, that means it's oh my bad, sorry. If it's greater than 0, it's minimum, and if it's less than 0, it's maximum. So there are some there are some restrictions when you can use second derivative. You cannot use second derivative when after double differentiation the function which you get it's not equal to 0. So this is a function when it's equal to 0. As you can see, there's no maxima minima in this. Sometimes it's undefined function. So in that cases you cannot use second derivative. You are forced to use first derivative. And the second point is when you want to observe the behavior of the values in intervals. In first derivative, as I said, you use intervals like RHS, LHS values to find out. So if you want to find out how the graph is behaving in those particular intervals, then I would advise you use first derivative, because second derivative doesn't use that. So this is a mnemonic which I came up with to remember easily the steps which you take to solve, to get maxima minima. So you can take it as a story. Once in a place there was a duke. He was very old and he didn't like much sound. He used to always live in a confined place in his room, away from all the noises. But the problem with his land was there were lot of pigeons and lot of crows also, which used to make lot of noise. So now he commanded all his soldiers and commandos to shoot down all those crows, all those pigeons, because he was getting irritated. But the condition was they are not supposed to use guns, because guns use noise. So now what the commandos, the smartest counselor or advisor, as you can say, what he taught is the duke's cat. Cats are known for their stealth, for their sleekness, how they attack. So what he said to the commandos is, the duke's cat catches pigeons silently. No need to use guns. So the D stands for differentiate with first derivative. You get the C, cat, critical points identification. Equate it to 0, you will get the critical point. Another C, catches. Check if the function is undefined. Now what will be undefined function? Everybody's question will be. So suppose you get a function as phi by x, where x is equal to 0. Phi by 0 is infinity. That function is undefined. You check that. Now you proceed with second derivative, the P for pigeons, and then the S. Sort the points into greater than or less than 0 to find out the local maxima minima. So yeah. So as I said, I'll give you some examples. This is a first example used by many businesses. So they use maxima minima to maximize profits and minimize cost. This is the objective of every business idea. Profit should be maximum and the cost which is required to get the material should be minimum. So example, company manufactures and sells a product. Its goal is to find the level of product, that is the number of units that it will produce, that will maximize profits but will reduce the cost. To do this, the company analyzes two main functions. We use functions now. Revenue function, that is how much it will generate, this income. the Rx, you denote it by Rx, represents the income from selling X units. X is a variable here. After selling this much amount of units, what is the revenue generated? And second is cost function, that is Cx. It represents a total cost of producing X units. Now to produce those units, you need some cost. That is represented by C of X. Now profit function is difference between revenue and cost. Simple logic. Profit is given by the revenue you generated minus cost. So yeah, that is what is applied here, Rx minus Cx. After you do that, so now let's take Rx as 50x minus x square. Now you will say, why is the function so complicated? It's in real life application, usually it's like this only. You will hardly find any simple functions. In fact, it's more complicated than this. And cost function as 10x plus 5. Now profit function, as I said, it's Rx minus Cx. You subtract Rx 50x minus x square minus 10x plus 5. Now after simplification, you will get answer as minus x square plus 40x minus 5 after subtracting, opening the brackets. Now you start with the first derivative. Take the first derivative. This is p of x. To get p dash x, after differentiation, normal differentiation rules, n minus 1, the x square, it becomes 2x, the formula x raised to n, where it becomes nx raised to n minus 1, that one, you will get 2x, 2 minus 1 is 1, so the exponent will be 1, and you get minus 2x plus 40, here x goes because it's x raised to 1, and constant becomes 0 in differentiation. You get p dash x as minus 2x plus 40. Now to get the critical points, set p dash x to 0. You set this to 0, 40 goes this side, minus 2x is equal to minus 40, x my negative sign gets cancelled, x is equal to 20. Now this is the value we got. Now to check if this is maxima or minima, you use second derivative, p double dash of x. Now I am not using first derivative here because it's usually time consuming, so yeah, I go with second derivative. P dash x, you after differentiating this function, p dash x, 40 goes because it's constant, and this you get answer as minus 2. Now as this is less than 0, if you remember the rules which I said, if the value you get is less than 0, then the point is a maxima point, and the value you get after substituting it in the function is the maximum value. So I can now safely substitute x is equal to 20 in this function, in any of these functions, this one, in p dash x, and you'll get answer as 395 rupees. So this is the maximum profit that the business can acquire by selling 20 units. You can calculate it by yourself. If it sells 21 rupees, the answer won't come 395. It will come around 394, 393. So 20 is the maximum value of the business, the units it can sell to attain this maximum profit. So the company maximizes its profit by producing 20 units. Beyond this level, increasing production would decrease profits, illustrating the use of maximum and profit optimization. You will get profits, but the profit won't be maximum, it will be less. Second example for environmental enthusiasts. So many factories nowadays, as you see in many countries, they are applying laws so that the pollution is reduced. There are certain norms followed by every factory so that the pollutions are reduced because it's not safe. Now what we'll think is the company should reduce its output so that the pollution also can be reduced. But this is not how a business will work. So what a company does is, again, we need to produce, we need to find out the maximum number of products which we can produce to get a minimum amount of pollution, the standards. So a story again. A factory's management decided to launch a green factory initiative. They aim to minimize the pollution output while maintaining production levels. Production is constant, but pollution is minimized. We need to find minima here. As you can see, it's a hint. Now, the function of pollution output could be modeled by a quadratic function. we get a function here for p of x. This is the pollution factor. 0.1 x square minus 5x plus 100. In this equation, P of x represents the total emissions, total pollution emissions, and x is the amount of energy consumed. This is the energy it consumes. So in a function, and the coefficients are like the how much by it's basically if the coefficients are more, that means the energy consumed is more, and if it's less, it's less, of course. Yeah. So again, we do the same thing. First derivative test, you differentiate it, you get minus 0.2x minus 5, because the x squared 2 goes 2 into 0.1 is 0.2. It's normal differentiation, you get this. Now you set this equal to 0 to get the critical points. You minus 5 goes there, 0.2x is equal to 5, x you get as 25 after taking the point to this side. Now we got this value, x is equal to 25. Now let's find out if this is maxima or minima or nothing. For this, second derivative test comes to our help. We again differentiated, double differentiation of this 0.2x minus 5. 5 goes away as it's a constant. You get e double dash of x as 0.2. So as this is greater than 0 according to the rules, the value x is equal to 25 is a local minima, and the value after substituting it in the function is the minimum value of pollution which can be generated. I mean not generated, which can be output. So this calculation gives us the minimum emissions at the optimal energy consumption level. So other interesting examples which you can see in healthcare, pharmacologist, the side effects should be minimum, and the effects of the dosage should be maximum. That is the primary output of any medicine. So they use maxima minima for this. Agriculture, farmers use maxima to determine optimal amount of fertilizers, that is minimum amount of fertilizers, water and other inputs that lead to the highest crop yield, maxima. And transportation and logistics, transportation companies use algorithms or functions to find the shortest or fastest routes to minimize fuel consumption and delivery times. Fuel consumption less, and the time taken should also be less. So conclusion, just a recap: maxima, highest point of a function in the graph; minima, the lowest point of a function, the concave down. Then graph of maximum minima is a parabola, and first and second derivative tests find maxima minima, the two methods which we learned. Then the mnemonic, Duke's cat catches pigeons silently, and concept of maxima minima has a lot of use in real life applications. So yeah, that's it for today. Thank you very much. Any questions? Yeah.
How exactly do we use critical points to find maxima and minima?
Critical points is like critical points is basically they are like coordinate points in the graph with which you can find out. Wait, let me just go to the slide so I can clarify more better. Yeah, so critical points are like they are like dummy values for the coordinate points in the graph. So critical points can be maxima or minima. We use the test to find if it's maxima or minima, like that. So yeah, critical points are basically the points. Yeah.
Could you move to the first slide, the first example?
First.
The one with the graph.
Oh yeah, 1 minute. This.
Wouldn't the absolute maximum here be infinity?
No, it's not actually possible, because after some time, when the graph goes up, like this, every graph, the maximum would be infinity and minimum also would be infinity, negative infinity. Because every graph, it goes up like straight infinity. As it's a parabola, it comes, as I said in the points, it comes to a point, maxima point, and then again goes to a minimum point, and then it just goes away. You can't catch it.
So in a parabola as well, if the parabola is opening downwards,
Yeah.
The minima would be minus infinity.
The minima, there won't be any minima. Minima and maxima concepts are not used with infinities. That's why we say it as local maxima. Local means there should be a point. The value can't be infinite. So yeah. Yeah.
Great presentation, by the way.
Oh, thanks.
But then we use first derivative, second derivative test to determine the nature of a function. Right?
Okay.
We said that based on the values we get from the first and second derivative function, we can judge how the graph or the function goes and find local maximum and minimum. But why do we use differentiation to find those set values to describe the function?
We use, okay, nice question. Okay. We use differentiation to find out those critical points because every time, this is first derivative, as the name suggests, you differentiate the question to get the derivative. After the derivatives get, you find the critical points. Yeah, so did I answer your question? I mean, I'm not sure.
Is there a different method to find the nature of the function without using differentiation? Like
Nature. Okay, another method is out of my scope because these are the methods which I know according to my knowledge. Yeah, but I can research more on this and tell you.
So you kindly note that there are also students like you. So don't go beyond the limit.
Yeah, you had a question? Yeah.
What is the significance of taking the point or the function is not defined as a critical point?
Yeah, when the function is not defined, there is no point of taking critical point. I mean, you can only find out the function is undefined by taking the critical points and then equate. Yeah, as I said here, just a minute. Yeah, you can only find out the function is undefined by taking the critical points and then equating it to 0 and all that. So till that, you need to continue solving it. Before that, only by seeing a graph, you can find out if the function is undefined. As one example which I gave here, yeah, so this is an undefined function. If you see at a graph, yeah, you don't need to use any of the methods. You can say, this function is undefined because it's just going up. There's no maximum minimum. But then now suppose if they give you a function x square minus 2x, you can't just say, oh, this is undefined function. You need to solve it by using this first derivative and second derivative, and then you can find out if this is undefined or not.